Hello everyone. I wanted to make a video lecture for Thursday's class. That's going to be October 17th. We won't have in-person class. I have some personal things that came up and I'm going to have to leave town. And I couldn't find anyone to fill in for me in class, so we're going to have to do it this way. So I'm really sorry about that. I know in person is better, and I tried to keep it that way, but kind of make and do with what we've got right now. So this will be the lecture for Thursday, October 17th. And just a reminder that the prerequisite review for Module 8 is due Thursday, which is October 17th. And your Module 8 homework assignment in Alex will be due on Monday. That is October 21st. Okay, so without further ado, let's get into it. So we talked about inverse trig functions on, gosh, what day was that? On Tuesday. That was yesterday. And we started to, we figured out that inverse trig functions have reduced domains, right? In order to have an inverse function, our regular functions needed to have a restricted domain. And so what that means is that our inverse trig functions can't see the entire unit circle. Inverse sine and inverse tangent can only see from negative pi over 2 down here to positive pi over 2 up here. They can see quadrants 1 and 4. And again, that's arcsine and arctangent. And again, old guys a long time ago stuck us with this negative pi over 2 to positive pi over 2, which means in this quadrant 4 down here, we need to use negatively rotating angles, just because that's kind of what we have to work with and the standard that they set for us. And then arc cosine, or inverse cosine, is a little bit different. Instead of being from negative pi over 2 to positive pi over 2, inverse cosine can see from 0, which is over here, to pi, which is over here. So inverse cosine can see quadrants 1 and 2. We don't have to worry about any negatively rotating angles there. It's all positively rotating in quadrants 1 and 2. Okay, so those are inverse trig functions, and we started parallel parking, which is when we have forward and backward trig functions in the same problem. And remember, parallel parking is hard. You have to take your time, go slowly, make sure your car is in, drive or in reverse. You have to make sure you're going the right way, and just go slow and take your time and make sure that you don't hit anything. So we didn't quite get to this number 6, but you have everything that you need to do that. So I just kind of popped the answer in here. Cosine of pi is going to be -1, and then inverse cosine is going to bring us back to pi, because from 0 to pi, pi is the only place where the cosine value is -1. Okay, so let's continue parallel parking, and we're going to be using all of that information to continue to do some problems. So now we've got some tangents involved, but we're still parallel parking. When you've got functions inside other functions, this is called function composition. You're going to start on the inside and you're going to work your way out. So we're going to start by doing the tangent of -3 pi over 4. And this is a forward trig function, so this is an angle. That -3 pi over 4 is an angle. So I'm going to go to my unit circle and I'm going to say, okay, where is -3 pi over 4? And remember, this is a negatively rotating angle. So if instead of being up in quadrant 2 with a +3 pi over 4, I'm going to rotate clockwise in the opposite direction for the same amount of distance, and I'm going to end in quadrant 3 down where 5 pi over 4 is. So 5 pi over 4 is coterminal with -3 pi over 4, and the tangent of that is going to be y over x there. So it's going to be -√2 over 2 over -√2 over 2. What's negative root 2 over 2 divided by negative root 2 over 2? Yeah, it's 1. It's something divided by itself, so that's going to give me a positive 1. And so that's what the inside simplifies to. And now I just have to finish my problem and then finish the arctangent of 1. Okay, so this is an inverse trig function. We're going backwards, which means this 1 is a ratio. This is coming from the ordered pairs on our unit circle. And because it's a positive ratio inside of arctangent, we're going to quadrant 1. And so I'm going to go to quadrant 1 on my unit circle, and I'm going to say, at what angle is y divided by x equal to 1? Right? Because again, tangent is y divided by x. So I'm going to look in quadrant 1, and I'm going to say, where is y divided by x equal to 1? Well, to get 1, I'm going to need something divided by itself. And you'll notice that y and x are only the same at pi over 4. So this is going to take us to positive pi over 4. That's in quadrant 1, so we don't have to worry about whether we're negatively rotating. Okay, so what if we start mixing functions together? Like in number 8, we have the inverse cosine of the tangent of 135 degrees. You might think it's going to be a bit harder when we start mixing trig functions, but honestly, our process isn't going to change. It's going to be exactly the same. We're going to start on the inside. We're going to work our way out. We're going to start figuring out if we're going forwards or backwards, and we're going to take our time. So we're going to start on the inside, and we're going to do the tangent of 135 degrees. Tangent is a forward trig function, so we put angles in, right? So we're putting the angle 135 degrees in, and I need to get the tangent value out. So I'm going to go to my unit circle to 135 degrees in quadrant 2. And it's tangent, so I'm going to do y divided by x in the ordered pair there. And we're going to get root 2 over 2, that's my y, divided by negative root 2 over 2, that's my x. What's root 2 over 2 divided by negative root 2 over 2? Yeah, it's negative 1. Okay, so we got negative 1 inside here, but we're not done with the problem because I still haven't done this backwards cosine function out here. So now we have to do the arc cosine of negative 1. Okay, so now we're dealing with cosine. And it's a backwards trig function, which means this negative 1 is the ratio. It's coming from the ordered pair. And it's negative, right? I've got a negative ratio inside arc cosine. So which quadrant is this going to take us to? Yep, it's going to go to quadrant 2. And so now I'm looking for the angle in quadrant 2 where the cosine value, x on the unit circle, is negative 1. Where on the unit circle between 0 and pi, and specifically in quadrant 2, is the cosine value equal to negative 1? Yep, it's over there at pi because that is negative 1, 0. That's from the x coordinate of my ordered pair is negative 1. So pi is the angle that will be returned to me here. Or I guess we started out in degrees, so I guess we'll end in degrees. Sorry. We'll do 180 degrees. Just because we started in degrees, I'll keep that the same, and we'll end it in degrees. Okay, so let's do some more. Let's do number 9. Inverse sine of negative 1/2. That's where we're going to start, right? We're going to start on the inside, and then we're going to have to do the cosine of that later. So first, we're going to start on the inside and do the inverse sine of negative 1/2. Okay, this is a backwards trig function, which means negative 1/2 is a ratio. Because it's a negative ratio, arc sine is going to take us to which quadrant? Yep, quadrant 4. Okay, so I'm looking for an angle in quadrant 4 that has a sine value, a y coordinate in the ordered pair of negative 1/2. Which angle in quadrant 4 has a sine value of negative 1/2? Yep, it's 11 pi over 6, right? But remember, in quadrant 4, old guys a long time ago stuck us with the fact that this needs to be negatively rotating. So instead of positive 11 pi over 6, we're going to write that as negative 1 pi over 6, right? That's the same, that's the negatively rotating angle that's coterminal. If you have a hard time logicking that out, just subtract 2 pi from that 11 pi over 6. So when you subtract 2 pi, that's the same as subtracting 12 pi over 6, and 11 pi over 6 minus 12 pi over 6 gives us that negative pi over 6. So whichever way your brain likes, you can go with that. Just make sure it's a negatively rotating angle in quadrant 4. Okay, so now that we've done the inside and we got negative pi over 6, we're still not quite done with this problem because we still have to pull forward into our spot, right? So we're going to take the cosine of negative pi over 6. This is a forward trig function, so now we're going to be looking at the angle of negative pi over 6. And remember, that's in quadrant 4. It's coterminal with 11 pi over 6, so that's where we're looking. And we're going to find the cosine value of that angle, which is the x-coordinate of its ordered pair. The x-coordinate there is root 3 over 2. Okay. Let's go ahead. I want you to pause the video and I want you to work through number 10 on your own here for a minute. So pause the video, work through that, and then hit play when you're ready. All right, hopefully you've had a chance to work through that. We are going to find the arc sine. If your brain doesn't like arc sine, you can replace that with inverse sine. Those mean the same thing. Of the cosine of 5 pi over 4. We're going to start on the inside and do the cosine of 5 pi over 4 first. This is a forward trig function. So 5 pi over 4 is an angle. So I'm going to be looking in the center of my unit circle for the angle 5 pi over 4. And you'll find that down here in quadrant 3. And we're looking for the cosine value, which is the x-coordinate of your ordered pair. And you'll find that the x-coordinate of the ordered pair there is negative root 2 over 2. Okay, that's the inside forward part. Now we have to finish this problem and do the outside backwards part. So now I'm taking the inverse sine of negative root 2 over 2. This is a backwards trig function, so this is a ratio inside there. And I have a negative ratio going into arc sine, so we're headed to quadrant 4. Yep. And remember, in quadrant 4, negatively rotating angles. So we are looking for the angle in quadrant 4 that has a sine value, a y-coordinate in the ordered pair of negative root 2 over 2. So you'll find the y-coordinate is negative root 2 over 2 at 7 pi over 4, but we can't write it as 7 pi over 4. We have to use the negatively rotating angle, and you can either use the negatively rotating angle or subtract 2 pi. Either way, you will get negative pi over 4. Okay, so our process really isn't changing here when we're mixing our trig functions. You're still just starting on the inside, working your way out, and being careful about which direction you're going. These next few is where it's going to get a little bit spicier. So let's see what changes as we continue on here. So number 11, the sine of inverse tangent of 3/4. Okay, this doesn't look any different. So we're going to do what we always do. We're going to start on the inside, and I'm going to say, okay, I'm doing a backwards trig function, which means 3/4 is my ratio. And so I'm looking for the angle that has a tangent ratio of 3 over 4. Because it's a positive ratio, arctangent is going to take us to quadrant 1. And so I'm looking for the angle in quadrant 1 that has a tangent value, y over x on my unit circle of 3/4. Which angle in quadrant 1 has a y over x of 3/4? Yeah, there isn't one. That's where this gets spicier. that ratio is not on the unit circle. So our unit circle is not going to help us figure out how to do this. So what we're going to do is when we aren't on the unit circle, we are going to draw a triangle. And we are going to draw our triangle in quadrant 1 because that is where arctangent is going to take us. So I'm going to draw an angle here in quadrant 1. And I know something about this reference triangle. I know that, right, this 3/4, this is a tangent ratio. It's the ratio of opposite over adjacent because that's the ratio that goes into inverse tangent. So I know that the opposite side of my reference angle here is 3. So this is 3. I know that the adjacent side of that angle is 4. So this is 4. Now we can do the Pythagorean theorem to kind of finish this all out. And we can do 3 squared plus 4 squared equals c squared, Pythagorean theorem. We are going to get that 9 plus 16 is c squared, which means c squared is 25. And that means that c is either plus or minus 5. Because c is the hypotenuse, it's always positive. That's going to be 5. Okay, so how does this help us answer the problem? Okay, so basically, when we do inverse tangent of 3/4, we are going to get the angle in quadrant 1 that has an opposite over adjacent ratio of 3/4, which is this angle right here. I'm going to call it theta. That is the angle that arctangent of 3/4 is going to spit out at me. Now, I could put that in my calculator, but that's not going to be exact. And I'm going to try to keep this exact. And honestly, I don't need to find what that angle is because to finish this problem, the answer is not theta. The answer is the sine of that angle, right? Because I still have to pull forward here and finish my function and finish my problem. So I'm going to take the sine of that angle. And now that I have a triangle, I know what the sine of that angle is. It's going to be the opposite over hypotenuse ratio. So it's going to be my opposite side of 3 over my hypotenuse of 5. This is going to be the ratio that is the answer to this question. So we really don't need to go to our calculators. We don't need to put anything in. We just need to draw a triangle, and we've got to put it in the right quadrant and make sure that we're careful with our signs. Okay, so let's try that again. Well, let's try another one, I suppose. Number 12, what if I have the tangent of the inverse cosine of -8 over 11? Again, we're going to start on the inside where we always do. And we're going to do the inverse cosine of -8 over 11. This is a backwards trig function, which means -8 over 11 is a ratio. It's the cosine ratio of adjacent over hypotenuse. And this is a negative ratio. If I put a negative ratio into arc cosine, what quadrant is this going to take me to? Yep, quadrant 2 is where inverse cosine goes with the negative. So we're going to get an angle in quadrant 2 that has a cosine value of -8 over 11. Now you can look at your unit circle. You're looking for -8 over 11 in the x coordinate on your unit circle. And you may already know you are not going to find it there. 8 over 11 does not live on the unit circle. So we're going to draw a triangle. And we are going to draw our triangle in quadrant 2. So again, we're going to draw a terminal side coming out of the origin, and we're going to drop an altitude down to our x-axis to draw our reference triangle. So inverse cosine is going to return to us this angle in quadrant 2 that has an inverse cosine ratio of -8 over 11. And remember, when we have an angle that's bigger than 90 degrees, we use our reference angle to kind of fill in this triangle. And this ratio is in inverse cosine, so I know that ratio is adjacent over hypotenuse. Now, where does that negative go? Does it go with the adjacent side or the hypotenuse? Well, the hypotenuse always has to be positive, so I know that my adjacent side is the one that's negative, and my hypotenuse is positive 11. So now I can fill these in. I know that my adjacent side is negative 8. My hypotenuse is 11. And so basically what we're going to do here is that inverse cosine is going to give us this angle, I'll call it theta, that rotates into quadrant 2, that has this reference triangle there. So theta, this angle, is what inverse cosine is going to return to me. But again, I don't need to find theta. To finish this problem, I need to find the tangent of theta. Okay, so I know that tangent is going to be opposite over adjacent, so I'm going to use my lovely triangle here to finish it, but I don't have the opposite side. So we're going to find it with a Pythagorean theorem. So I'm going to do negative 8 squared plus my opposite side squared is going to be my hypotenuse squared. So 64 plus b squared is going to be 121. Not going to lie, my brain does not want to do that right now. So I'm going to take out my handy dandy TI-30 X2S and I'm going to make it do that for me. So 121 minus 64 is 57. So I know that b squared is 57, which means that b is plus or minus the square root of 57. Now we're going to have to look at our triangle and figure out, is this going to be a positive 57 or a negative 57? Yep, it's positive because in quadrant 2, our vertical y value is positive, and so this is going to be positive square root of 57. And now I can finish this and I can take the tangent of my reference angle here, and I'm going to do the opposite side, which is the square root of 57, over the adjacent side, which is negative 8, and that is going to be the ratio that is the answer to this problem. All right. So I want you to work through numbers 13 and 14 on your own, and I want you to pay attention to whether you need the unit circle or whether you need to draw a triangle in each of those, because that's going to be a tough thing that you're going to have to kind of work through on a quiz or a test. I'm not going to tell you which ones you need the unit circle for and which ones you don't, so I want you to focus on that and figure out whether you need a triangle or whether you're going to use your unit circle. So go ahead and do those and hit play when you're ready. All right, hopefully you've had a chance to work on those. So let's start with number 13. We're going to do the sine of inverse cosine of root 3 over 2. So we're going to start on the inside and work our way out. Okay, inverse cosine, that's a backwards cosine, which means I know that this root 3 over 2 is a ratio. It's going to either be in the ordered pairs in my unit circle, or it's going to help me fill in my triangle. Because it's a positive ratio, arc cosine is going to take us to quadrant 1. So the first thing that I'm going to do, our first line of defense, is the unit circle. I'm going to look at the unit circle and say, do I have a cosine value, an x coordinate, of square root of 3 over 2 in any of my ordered pairs in quadrant 1? And the answer is yes. This one lives on the unit circle. So we can kind of do our happy dance and say, oh, this one's going to be a little simpler. I'm just going to go to my unit circle and kind of work this out. So what angle in quadrant 1 has a cosine value of root 3 over 2? Yep, it's pi over 6. And now to finish the problem, we have to take the sine of that pi over 6. What's the sine value of pi over 6? What's the y coordinate at that angle? Yep, it is 1/2. And we have completed that problem. So that one was on the unit circle when we didn't need to draw a triangle for it. How about number 4? Okay, cosine of arctangent of 2. And again, arctangent, if you don't like that notation, you can put that into inverse tangent if you like. And we're going to start on the inside. I'm taking the inverse tangent of 2, which means I'm looking for a ratio of 2. And this is a positive ratio, which means arctangent is going to take us to quadrant 1. Yep. And in quadrant 1, I'm looking for a tangent ratio of 2. Y divided by x, that gives me 2. Does that live on the unit circle? No. If you do y divided by x in all of those ordered pairs in quadrant 1, you're either going to get root 3, 1 over root 3, or 1. We don't get 2. So what do? We draw a triangle. Where are we drawing our triangle? In quadrant 1. So I'm drawing a terminal side in quadrant 1. I'm dropping it down to the x-axis, and I'm marking this is going to be my angle theta, and it's going to be my reference angle in quadrant 1. It's kind of the same thing. And so I know that this angle in quadrant 1 needs to have a tangent ratio of 2. Okay, well, I know that tangent gives me the opposite over adjacent ratio, so I need this to be 2, which means 2 over 1. We can write it as a fraction so that we can see all of those sides. And notice that this means that our opposite side is 2, so I'll fill that in, and our adjacent side is 1, so I'll fill that one in. Okay, cool. Now we have a triangle. And when I do the arctangent of 2, it's going to take me to this angle theta here in quadrant 1 that has a tangent value of 2. So this is going to return the angle theta for me, and now I have to take the cosine of that angle. Well, to find the cosine of that angle, I need to do adjacent over hypotenuse. And I don't have the hypotenuse, so we're going to do the Pythagorean theorem. 1 squared plus 2 squared equals c squared, which means that 1 plus 4 is c squared, and this c squared is 5, which means c is going to be plus or minus the square root of 5. And it's positive because it's a hypotenuse, which means this is the positive square root of 5. So what's the cosine of theta? What's the answer to this problem? It's the adjacent side of 1 over the hypotenuse of root 5. Okay. Okay, so hopefully you feel good about when to use the triangles and when to use the unit circle. And we've got one last level of spiciness here. We are looking now at things that look like what we just did, but they have variables in them, guys. We're not going to panic. We are going to continue the course. We are going to trust our process. We are going to follow our gut, and we're going to follow our processes. Here we go. I'm looking for the cotangent of the inverse sine of 4v. V is a variable. We're going to assume that it's positive, just to kind of keep everything, I guess, simpler. Alex isn't going to tell you that those variables are positive, but I want you to assume that those variables are positive. It's just going to simplify your life a little bit and make things easier for you. So we're going to assume that V is positive. So we're taking the inverse sine of 4V. Okay, that means this is a backwards trig function. So 4V is a ratio. And since V is positive, 4 times V is positive, which means arcsine is going to return us to quadrant 1, right? Okay, cool. So I'm looking for the angle in quadrant 1 that has a sine ratio, a y value on the unit circle of 4V. Are you going to find 4V on the unit circle in those ordered pairs? Yeah, definitely not. So we're going to do what? Draw a triangle. If we're not on the unit circle, you are going to draw yourself a triangle. And we're going to draw ourselves a triangle in quadrant 1 because 4V is positive, or we're assuming that to make our lives a little bit easier. And now I can kind of start to fill in my triangle. This 4V is a sine ratio, so it's the ratio of opposite over hypotenuse. And again, we're going to write this as a fraction so that we can kind of process this a little bit better. 4V is the same as 4V over 1, right? Okay, so that's my opposite over hypotenuse ratio. Don't overthink it. Don't panic. We're just going to put it in our triangle. So our opposite side, here's my reference angle. Our opposite side is 4V. My hypotenuse is 1. And we'll go ahead and figure out what this adjacent side is using the Pythagorean theorem. So my adjacent side squared plus my opposite side, which is 4V, the whole thing squared, equals 1 squared. Okay, now I know we've got several variables in here, and so that we don't get confused, I'm going to put a little box around the A to say this is the one I'm solving for. I know there's a V in there. We're not going to panic. We're going to let it be what it is, but A is the one that I'm solving for. So I'm going to kind of square that 4V, and I'm going to get 16V squared. When I square 1, I still get 1. Again, I'm just going to help myself keep track of that this is the one that I'm solving for. So how do we start getting A by itself? Yep, just like usual, you're going to subtract that 16V to the other side. 1 minus 16V squared. If you still need that box around the A, go ahead and put it there, but that's what we're solving for. So to get A by itself, you're going to take the square root of both sides. So we're going to have plus or minus the square root of 1 minus 16V squared. Is this positive or negative here in quadrant 1? Yep, everything in quadrant 1 is positive, so I'm just going to put the positive 1 minus 16V squared in there. Okay, so I know this triangle got a little uglier than usual, but it's still just a triangle. And so now we're going to follow our processes. When we take the inverse sine of 4V, what we're going to get is this angle here in quadrant 1. I'm going to call it theta, that has this triangle situation. So it's going to return to me that angle theta. And then to finish the problem, I'm going to have to take the cotangent of that angle theta. And so cotangent is going to give me the ratio of adjacent over opposite, right? It's tangent, but upside down. And so what's my adjacent side? Yep, it is the square root of 1 minus 16V squared over my opposite side, which is, you got it, 4V. This is the answer to the problem. You'll put it into Alex just like that. You're not going to solve for anything. You're not going to plug anything in. You're going to leave it with the V's in it. And it's going to say your answer should contain the variable V. So that'll kind of help give you a clue that you are on the right track. I know it looks weird. I know it feels kind of gross. Just put it in and trust your gut and trust your processes. All right, let's do one more of these so that you feel a little bit better about this. Again, we are not reinventing anything. We're not doing anything different. We are just going through our process. So if we do the cosine of the tangent inverse of u, we're going to start on the inside and do the inverse tangent of u first. Okay, that's an inverse trig function, which means u is my ratio. I'm assuming that u is positive, so when I put a positive ratio into arctangent, I'm going to quadrant 1. Okay, so when I put the ratio of u into inverse tangent, it's going to take me to an angle in quadrant 1 that has a tangent value of u over 1. Is that on the unit circle? No. So you're going to draw a triangle in quadrant 1. Here's my reference angle. And I know that the ratio in here is a tangent ratio. A tangent ratio is opposite over adjacent. So my opposite over adjacent has to be u or u over 1. So I want you to go ahead, pause the video, fill in your triangle, solve for that missing side, and finish the problem. Yes, you can. Hit play when you're ready. All right, hopefully you've had a chance to do that. When we fill this in, our opposite side here is u. Our adjacent side here is 1. And then we are going to do the Pythagorean theorem to get the length of our hypotenuse. So we will have 1 squared plus u squared equals c squared. And again, we've got multiple variables flying around here. Which is the one that I'm solving for here? I'm trying to figure out what the hypotenuse is, which is c. So this is the one that I'm solving for. So I'm just going to help myself keep track of that. And so when I square everything, I'm going to get 1 plus u squared equals c squared. Again, c is the one that I'm solving for, and we're almost there. How do you get c by itself? Yeah, you're going to take the square root of both sides, which means that c is either plus or minus the square root of 1 plus u squared. Is it going to be positive or negative? Yep, it's a hypotenuse, so it's going to be positive. So this is going to be the square root of 1 plus u squared. Now we have our triangle. Inverse tangent of u is going to take me to the angle in quadrant 1, which is this one, that has this triangle. So it's going to take me to that angle theta. And then I have to take the cosine of that angle theta, and I'm going to use my triangle to do that. Cosine gives me the adjacent over hypotenuse ratio. Our adjacent side is 1. Our hypotenuse is the square root of 1 plus u squared. And we have finished this problem. It has u's in it. Don't panic. That's how these guys work. And that, my friends, is Module 8. So Module 8 homework is due on Monday, which is October, I just told you this before, but I now have to look, 21st. October 21st is the Monday when this is due. And just to help ourselves, I've got a little bit of time left here to help ourselves with the next module in Module 9. We're going to go ahead and get started because Module 9, I think modules 9 and 10 are probably some of the most difficult in this course. So I want to make sure that we've got plenty of time to work through those at a pace that will help. And really what makes modules 9 and 10 so difficult is that we are we're starting to do algebra and trig together. And I think that's the really hard thing about this. So let's get into Module 9. This is the first part of a trigonometric identities section. Module 10 will be our second part. And there are only 2 parts, so that's the good news. But we're going to start coming up with trigonometric identities. Now, before we get into our trigonometric identities, I want to tell you what an identity is. So an identity in math is, let me see if I can write here, is an equation that is always true for any value of your variable. I'm usually going to say x, but it can really be whatever variable is in there. It's always true for any any value of your input variable. Okay, so for instance, kind of the classic identity is that x is equal to x. It doesn't matter what number you put in there for x. Any number is equal to itself, right? 2 is equal to 2. 0 is equal to 0. Pi is equal to pi. Negative 37 is equal to negative 37, right? 114.798 is equal to 114.798. You can literally put anything in there, and this is always going to be true. So that's kind of our classic example of an identity. And we have a lot of them for trig. And we're going to use these to rewrite trig functions, because sometimes working with trig functions isn't the easiest thing in the world. And if we can rewrite it and kind of change the structure of it to look a little bit different, it'll be easier for our brains to process and work with. So we already have a lot of identities. We just haven't really put that name on them. So the first set of identities that we have are reciprocal identities. These come from our reciprocal functions, like cosecant and secant and cotangent. These are our reciprocal functions, right? Well, you already know the functions that these are the reciprocals of. Cosecant is the reciprocal of sine. So we're just going to write that cosecant is the reciprocal of sine. We're just going to do it in a mathy way. The way that we write the reciprocal of sine is going to be 1 over sine of theta. That's just how we represent a reciprocal, right? Because if you divide by something, you're going to multiply by its reciprocal. So cosecant is the reciprocal of sine. This is how we write it mathematically. So let's fill the rest of these in. Secant is the reciprocal of cosine. So we can write that as secant theta is equal to 1 over the cosine of theta. And cotangent is the reciprocal of tangent, and so we can write that as 1 over tangent of theta. Cool. And I know that we pretty much just use the reciprocal functions for cosecant, secant, and cotangent, but we can also do it for the big three as well. So we actually have 6 reciprocal identities. We have one for every one of our trig functions. Sine is the reciprocal of which function? Yep, it's the reciprocal of cosecant, just the same way that cosecant is the reciprocal of sine. So we can write that sine is 1 over the cosecant of theta. We can write that cosine of theta is the reciprocal of, yep, secant theta, just the way that secant is the reciprocal of cosine. And we can write that tangent is the reciprocal of cotangent of theta, just the same way that cotangent is the reciprocal of tangent. Okay, those are our reciprocal identities. We have 6 of them. And it doesn't matter what angle you put in there. You could put pi over 2. You could put pi over 6. You could put 7 pi over 4. You could put negative 3 pi over 4. You could put an angle that's not even on our unit circle. You could put 2 pi over 5 in there and put it in your calculator, and you will find that both sides of these equations are always the same, no matter what angle you put in there. It's an identity. And we also have even and odd identities. These come from the definition of an even and odd function and knowing which functions are even and which ones are odd. So which of our trig functions are even? Yep, it's just cosine and its reciprocal function of secant. And the definition of an even function says if I put a negative value into there, I get exactly the same thing out as if I had put a positive in. This is basically just using the definition of what it means to be an even function with our even functions. Okay, and then which ones are odd? Yep, the rest of them. So that means that sine is odd, and tangent is odd, and cosecant is odd, and cotangent is odd. And again, the definition of an odd function says if we put a negative into each of these functions, what happens when you put a negative into an odd function? Yep, it comes out front. So the sine of negative theta is equal to negative sine theta. The tangent of negative theta is the negative of the tangent of positive theta. Cosecant of negative theta is the negative cosecant of positive theta. And cotangent of negative theta is negative cotangent of theta. Again, these are our the definition of an odd function just applied to all of our odd functions. And these are all true no matter what angle you put in there. Always true. Okay, so those are our reciprocal identities and our even and odd identities. We'll practice how to use these in a little bit. And just to preface you on these, you will need to memorize these. But again, with what we have so far, these are really just things we already know. You just kind of have to remember how to write them. That cosecant is the reciprocal of sine, it's 1 over sine, right? Cosine is an even function, and an even function means if you put a negative in, it just poof disappears. So you're going to have to memorize these, but hopefully that's all things that are already in there. All right, we're going to get 2 more sets of identities here. And these come from our knowledge of the unit circle. And remember that if we have an ordered pair, x, y, if it's on the unit circle, then it has to satisfy the equation of a circle, which is x squared plus y squared equals r squared. And because it's a unit circle, that means our radius is 1. So this is the one that's always true on the unit circle. So any ordered pair on the unit circle has to satisfy this equation. We also know that on the unit circle, cosine of theta is our x-coordinate, sine of theta is our y-coordinate. To find the tangent of theta, you do y over x, and to find the cotangent of theta, you do x over y. Okay, so these are just kind of reminding us of things that we already know, and we are going to use these to find some new identities. We are going to start with our quotient identities, and those come from putting these tangent and cotangent equations together along with the cosine and sine values. So on the unit circle, y is my sine value and x is my cosine value. So let's think about that and say, okay, well, tangent is my y value divided by my x value, but the y value is the sine of theta. So I can replace y with sine of theta because that's really the same thing. And on the bottom here, instead of x is just cosine theta. So I could put cosine theta in there for x. And what we've just done is created a quotient identity. Tangent of theta is equal to sine of theta divided by cosine of theta. That's our first quotient identity, and it comes directly from the way that the unit circle works, right? So we can do that directly from the unit circle. And we can do the same thing with cotangent. Again, x up here, we're going to replace x with cosine of theta. So this time cosine of theta is going to go on the top. And we can replace this y on the bottom with sine of theta. So I'm going to put that sine of theta here on the bottom. And we have our second quotient identity that the cotangent of theta is the cosine of theta divided by the sine of theta. These are our quotient identities. And there's just 2 of them. Okay, and then remember, you can always work these back out from your unit circle. You already know that tangent is y over x on your unit circle. You know that x is cosine and y is sine. Put it together on your unit circle, and then cotangent is the reciprocal of tangent, so you can also just turn that upside down. So again, you'll have to memorize these, but they're putting together things that you already know. So don't panic. You can figure these out on your exam if you need to. Okay, and then the next set is our Pythagorean identities. Those are going to come from this equation of the unit circle and putting that together with our sine and cosine from the unit circle. So our first identity here says that x squared, but again, x on the unit circle is cosine. So I can put cosine of theta in there for x. So if I have cosine theta squared, and I add to that y squared, but y is sine theta. So I'm going to put sine of theta in there for y. And so now I have x squared plus y squared, which turns into cosine squared, or cosine of theta squared plus sine of theta squared. And because I'm on the unit circle, this has to equal 1. We're going to fix that notation a little bit. We don't usually leave the squared on the outside just because it gets confusing. So I'm going to put that up here where we normally see it and write it this way. So we have that our Pythagorean identity is that the cosine squared of theta plus sine squared of theta equals 1. This is our first Pythagorean identity. Now we are going to have 2 more forms of this. And again, you're going to have to memorize these, but I don't want you to panic because if you know this one, it's pretty easy to get to the other ones. To get to our second version here, I want you to divide everything by cosine squared of theta. So if I divide everything in there by cosine squared of theta, what I'm going to get is cosine squared of theta divided by cosine squared of theta. Sorry, sometimes I put the parentheses and sometimes I don't. Technically, you don't need the parentheses. I just like to do that to remind you that there's an argument there and that those things are connected. So if I divide sine squared by cosine squared, that's what we end up with. And we're dividing everything, which includes that 1 as well, by cosine squared of theta. Now we're going to simplify this. So if I take cosine squared divided by cosine squared, anything divided by itself is 1. Plus sine squared divided by cosine squared. Well, I know that sine over cosine is tangent. So it should make sense that sine squared over cosine squared gives me tangent squared of theta. If you're having trouble seeing that, you can always think about that as being the sine of theta over the cosine of theta, that entire thing squared, right? These two notations mean the same thing. So that can also help you get to tangent squared if you are having trouble with keeping them separated. Okay, and then our last one, 1 over cosine squared. Well, that's the reciprocal of cosine squared. The reciprocal of cosine is secant, so 1 over cosine squared will be secant squared of theta. This is the second form of our Pythagorean identities. And again, if you're having trouble seeing that secant of theta, this is the same thing as 1 over the cosine of theta, that whole thing squared, which is how we get to secant squared, if that helps your brain a little bit. Okay, that's the second form of the Pythagorean identity. 1 plus tangent squared of theta is equal to secant squared of theta. And to get our third form, we're going to come back to our OG here. And instead of dividing by cosine squared, we are going to divide by sine squared. So when I take everything in that OG and divide by sine squared, I get cosine squared of theta over sine squared of theta plus sine squared of theta over sine squared of theta equals 1 over sine squared of theta. And now the last thing that we have to do is simplify. Cosine squared over sine squared. Well, that's cosine over sine, that whole thing squared. Cosine of theta divided by sine of theta is cotangent. This is cotangent squared of theta. Plus sine squared divided by sine squared. Anything divided by itself is 1. And then on this side, 1 over sine squared of theta. That's the reciprocal of sine squared, which is cosecant squared of theta. And this is your third version of your Pythagorean identities. Okay, so these are all of our first sets of identities. Again, you are going to have to memorize all of these, your reciprocal identities, your even and odd identities, your quotient identities, and your Pythagorean identities. You're also going to need to know which one is which, and tell me if you're using this identity that you used a quotient identity. We'll get into that a little bit, but I also want you to make sure that you know which of these identities falls under which, I guess, heading or title. Okay. I want to do a couple of examples of how we're going to use these, and then we're going to come back to this on Tuesday. So these are all of our identities. Every single one of these is true for any value of our variable and any angle you want. So we are going to use these to rewrite or simplify certain expressions that are in trig. So here's some helpful strategies to help you figure out when to do things. The first thing that I want you to do, your first line of defense, is to turn everything into sines and cosines. That's going to make it easier for you to see what things you can combine or what things that you can cancel, because when everything is in the same trig function, you can see where things combine or go away. And notice we can bring every other trig function in terms of sine and cosine. Cosecants can come to sines. Secants can come to cosines. Tangents can go to sines and cosines. Cotangents can go to cosines and sines. We can turn everything into sines and cosines, so we can always come back there. So that's going to be your first line of defense. Second thing that I want you to keep in mind is that we can rearrange these identities to fit our situation. These identities are equations after all. And really the main place where you're going to use this is with your Pythagorean identities. So our main Pythagorean identity says that cosine squared of theta plus sine squared of theta is equal to 1. But this is an equation. I can rearrange things. If I wanted to, I could rearrange this and subtract cosine squared from both sides. In that case, I would only have sine squared of theta left on this side. And on the other side, I would have 1 minus cosine squared of theta. Technically, these two are the same equation. I'm just moving things around. Alternatively, what if instead of subtracting cosine squared from both sides, what if I had subtracted this sine squared from both sides? Then I could get cosine squared of theta would be left over here. On the other side, I would have 1 minus sine squared of theta. Sorry, I'm like right at the edge. That says sine squared of theta. I'm going to try to slide this over so we can get everything on there. Sorry about that. So we have cosine squared over here, 1 minus sine squared of theta on the other side. Okay. Sorry that that's so tiny, but we can basically add or subtract things to both sides and move things around. You could multiply by negatives. You can really kind of do whatever you want. And so we are going to have to rearrange this occasionally to make it match what we've got in our problems. So keep in mind that you can rearrange those. And don't forget all of your algebra tricks. To add or subtract fractions, you need a common denominator. If you multiply fractions, you can multiply things in different orders. So because when we multiply fractions, we multiply straight across. So if I have something like x over y times z, I could kind of pull this out and rearrange things a little bit. I could write that as x times y, or sorry, x over y times 1 over z, right? I can pull that apart because when I multiplied across, I would still get x by itself on top and y times z on the bottom. If I wanted to, I could put the x over the z, right? I could also write that as 1 over y times x over z. We can really put this in any order that we wanted to and kind of rearrange as long as it's multiplication, right? You can switch orders of things with multiplication of fractions. So that's something that's going to help us. You can multiply by a conjugate if you need to. Remember that if you have something that looks like a plus b, its conjugate is a minus b. And so really anytime that you have addition or subtraction in a fraction, sometimes a conjugate can be a good option for you, and it's going to help us simplify things. And we're mainly going to use that to get into the Pythagorean identities, and that'll make sense later. If you have fractions within fractions, you want to keep change flipped to simplify that. But before you do that, you have to get a single fraction on top and a single fraction on the bottom. And factoring. We are also going to use factoring to help us out. So you don't necessarily need to memorize all of these, but if you get stuck on some of these problems and you think, I have no idea what I'm supposed to do, I want you to come back to this toolbox and I want you to go down the list and I want you to try things that would apply. You can say, oh, well, I've already tried to put everything in sine and cosine and I can't figure it out. So maybe you can try rearranging some of your identities to see if you can get it to look like something that you have in your problem. Maybe you can multiply things in different orders and pull them apart to make other functions. And just this is your toolbox. So when you get stuck, come back here. We will do one problem real quick, maybe two, we'll see. And then I'm going to let you go. All right, so our first problem here is we are looking to simplify each expression. Now, I know this one's going to feel kind of like you don't have a lot of direction. We're just trying to simplify this. So we are trying to see things that combine or cancel. And the main tool that we're going to use here is trying to turn everything into sines and cosines to combine and cancel and simplify. Okay, so cotangent of x times the secant of x. We're just going to try to make this look different and simplify it. And again, first line of defense is let's turn everything into sines and cosines. So let's start with cotangent. How do we turn cotangent of x into sines and cosines? We can come back to our list here. Cotangent, right here, are quotient identities. We can use this quotient identity to turn cotangent of x into sines and cosines. So cotangent is cosine over sine. So I'm going to turn cotangent of x into the cosine of x divided by the sine of x, right? I can do that. And what kind of identity did I just apply? Right? This was a quotient identity. I'm going to write these out because there's going to be, sometimes in ALEKS, you're going to have to write these out and sometimes you're not. And so I'm just going to get in the habit of writing them out. Okay, and then we also have secant of x. We could turn that into sines and cosines. How do I turn the secant of x into sines and cosines? Right here, secant is the reciprocal of cosine. So that's how I'm going to rewrite that one. And I'm going to write that secant is 1 over cosine of x, right? It's the reciprocal of cosine of x. And then I'm going to leave this one as the cosine of x over the sine of x, just like we had written it before. And then I'm just going to make a note that what the change that we made was right here, and we used a reciprocal identity for that. Okay. So now here's where it gets harder. We've turned everything into sines and cosines, and now we're just looking to algebra this to try to get something to simplify. So it will be simplified when you've combined things or canceled things. So let's see if we can combine or cancel anything. What do you see? Yeah, I have a cosine on the top and a cosine on the bottom. And those are connected only by multiplication, which means cancel them. And so once we cancel those, which we can do because of algebra, what we have left is a 1 on top and a sign of x on the bottom. And just to keep track of what we're doing here from the top, from that last step to this one, we just did algebra. We did some canceling. I'll write that. You don't have to write this, but just to keep track so that when you come back later, you can say, oh yeah, that's what we did. And we're not quite done because 1 over sine of x, we're trying, can we get that into a simpler form or just like a trig function on its own? Come back to here. Do you see 1 over sine of x anywhere? Oh yeah, right here, 1 over sine. We can write that as its reciprocal function, cosecant, right? 1 over sine is the reciprocal of sine. That is cosecant of x. That is as simplified as we can go. We have a trig function all by itself. We are done. As simplified as we go. And as we're simplifying, it may be a little less obvious exactly when you're done, but most of the time you're either going to get a number by itself or a single trig function by itself, and that's how you know you're going to be simplified. So that's where we're going to stop here, and we'll come back and we'll continue to simplify and we'll continue to use our identities. So come back on Tuesday, make sure you have your identities in front of you, and we're going to start working on using them to simplify. All right, I hope you have a great week ahead, and I will see you next week on Tuesday.